Hi, welcome back to our machine learning course. Now we've seen how to build convolutional neural networks. Let's look now at some famous examples of models and see what we can learn from them. And so we'll look at three examples right now. The first of them is VGG16. VGG is a research group, and they built this model in 2016 already, it's a long time ago. And this was one of the first deep convolutional networks. So a couple of reasons why they could build their network so deep. First of all, if you look at the architecture, it uses convolution layers and also uses max pooling a lot. So it starts with two blocks of two convolution layers and a max pooling, and then three blocks of three convolutional layers and max pooling. What max pooling does is it reduces your dimensionality quite drastically as you go deeper. And this allows you to, well, in the first hand, by reducing the spatial dimensions, you reduce the number of weights you need to learn, right? So your filters are have less work, can be less, so you have fewer weights to learn, so you can build the network deeper. Another thing it does, it uses only small filters, only 3x3 filters, and that again reduces the number of weights that you can learn. And this, but in that time, this was sort of how deep you could potentially learn neural architectures, given the computational resources available at the time. You reduce the number of spatial dimensions by making clever use of max pooling. Max pooling, like I said, reduces the spatial dimension. You don't want to do it every convolutional layer, otherwise you would have no well, you would be out of pixels like halfway network. You don't want that, so you want to do only max pooling after so many convolutional layers. Yeah, and then you find the best balance between them. Right? At the end, you have three convolutional fully connected layers, then softmax, and then this was trained on ImageNet, so it means you have 1,000 output classes. There's also an important thing to know, like all of these models we'll discuss right now, they were all basically designed to work well on ImageNet. ImageNet being this large data set of all images from the internet, 1,000 classes, a lot of variance, a lot of noise as well. So these models had to deal with learning this very high variance set of images, right? And on one hand, the low resolution that you enforce here with max pooling also forces the model to learn more robust features, so they're less sensitive to small changes in the input. Yeah, so this is VGG. A big downside, though, is that it only has these small filters. Now, if you have an image where you have, say, a large tree here and small flowers here, and you want to be able to capture both very small patterns and very large patterns, you can't just stick with small filters. So you want to have large and small filters combined. And this is solved by the next model called Inception. So what Inception does is, after the start is quite similar. So convolutional layers, max pooling, convolutional layers, max pooling. But then, instead of having only 3x3, what it does effectively is split up into, say, a 3x3, a 5x5, and a 7x7, and then concatenating basically the results of those three convolutional layers, right? With some tricks to make sure this can fit, right? But that's the idea. And so by combining this, you can actually learn small patterns and large patterns at the same time. Right? There's a number of other tricks. So that's basically the idea here. Now, you can see it's a bit more complicated than that, but I'll come back to that. So after you've done that, you end up with this very, very large hypertensor, right? So you want to then reduce this to, again, a smaller tensor. And you do that by doing convolution switched writing. So the reduction blocks, they combine striding, 3 by 3 stride 2. This is a convolution and then a convolution with striding. And this is just a max pooling that you add on top of this. And so this max pooling kind of tries to maintain the information, again, adding more to the field, of course, but still reducing the size of this very large output tensor that's the result of this normal block. Okay. And so this is the whole architecture. So first, traditional convolution layers, then 3 times of this combined normal block reduction, 4 times normal block reduction, 2 times normal block. It's a variation on it, it's very similar. And then at the end, average pooling, dropout, fully connected, and softmax. And then again, our ImageNet data set with 1,000 classes. Okay, few more things here. First of all, as you see, this is not a normal 3 by 3. This is actually a 1 by 1, 1 by 3, and 3 by 1. And this is called a factorized convolution. And this is explained a bit more here. So in a normal 3 by 3 convolutional kernel, this is your 3 by 3 convolutional kernel. And you would like move this over the image. This is your output, this is the input, this is the output. Now what you can do instead, just as you can decompose a matrix into 2 smaller matrices where you can choose the rank, what you can do is you can take your 3 by 3 kernel and decompose that into a 3 by 1 kernel and a 1 by 3 kernel. And mathematically, they will be identical. The weights values will be different, but mathematically, if you would have known the kernel, you could just have decomposed it into a 3 by 1 and 1 by 2 kernel and have the exact same result. Right? So you might as well learn these guys directly. And this is what happens here with these factorized convolutions. If you want to imagine what this looks like, this is shown here. This is again my input matrix, right? And so first I do this 1 by 3 convolution, so I get this funny 3 by 5 intermediate state, and then I do a 3 by 1 convolution, and again I get the same output 3 by 3. Right? And the upshot, however, is this has 9 parameters and this has 6 parameters, so it's much more efficient in terms of weights to learn. Right. And so this is what happens here. And a 5 by 5, by the way, you can decompose it into a 3 by 3 and a 3 by 3. And so you can decompose a 5 by 5 actually by doing uh, 1 by 1, 1 by 3, 3 by 1, 1 by 3, and 3 by 1. And this is identical to doing a 5 by 5. One more thing you may have noticed are these 1 by 1 convolutions. Now 1 by 1 convolutions or network layers, they just help you control the number of layers that you want. So say after all these, combining all these branches into this complex combined concatenated outputs tensor, you may have a lot of channels here, right? And you may want to reduce that. And so you can reduce it easily by doing n by n filter. So say here you have 64 outputs and you want to have only only 32 of them, then you can just do a 1 by 1 convolution and choose 32 of those guys, right? And so The inputs won't change, but the number of channels will. So you kind of average over the channels so that you have the number of channels that you want. That's why one convolution is basically help you control the shape of your tensors, so that you can make sure that as you go deeper into your network, you keep more or less the same shape, or you will reduce it probably, right? But you can control what these look like. So first of all, you can append them easily, and you can control the number of channels that you have as you go deeper in network. So you can actually combine all these different convolutions without going overboard. Okay. One more thing, this network has a problem in terms of vanishing gradients, because as you compute the loss here, well, first of all, imagine you have to do this for 2 layers, then reduction layers, then 4 normal blocks, reduction block, and non-normal 3 blocks, and then again your convolutional layers. So this is a very deep network, and it will suffer from vanishing gradients. Now to avoid that, they added this auxiliary classifier. So this will take the intermediate output, do some convolutions, do a fully connected layer, do a softmax to get an output, a rough output, and from that get some kind of loss, and then you can also backpropagate that loss to the network. And this will compensate for, like, the gradients here will be very small, but these ones might be larger. And so you still have enough signal to also train the deeper parts of your network thanks to this auxiliary classification head. It's not the most elegant approach, and I think after Inception very few models actually use this, because this problem is solved in the next model, which is called a ResNet. A ResNet adds one very important innovation, and that's the residual or the skip connection. What this does, it takes, well, first of all, starts again with convolutional max pooling, then does basically a 3 by 3 convolution, and so say this is your output, and then it takes the original input before you do the 3 by 3 convolution, you do striding over that. This is this is initial bit of a reduction block anyway. Okay, you take the output, and then what you do is you sum them up. So you don't concatenate, you sum it up element-wise, right? And then you get the output tensor. And so this one combines the original values, activations, with the ones you've learned after the convolution. And then you do the same thing over and over again. So here again, you take this input here, right? You do the convolution, 3 by 3 convolution. You have some output. And then you add this again to my skip connection, add this sum, right, to get the output here. That's my output. And then I'm going to do this over and over and over again. So these residual layers make sure that information does not get destroyed or lost during the convolution layers. Information can bypass multiple layers. And the main thing that this does is reducing vanishing gradients, right? So if you now have a loss, normally it would have to go to all these little layers, but now because you have skip connections, the gradients can actually skip over multiple layers, right, without actually seeing many convolution layers. And so this allows gradients to go very, very deep back into network, which allows you to build very, very, very deep neural networks. This is ResNet 50, but you also have ResNet 150, which is 150 layers. Right? That's the main innovation. You can build very, very deep neural networks, and overall, if you can build a deeper neural network, it will typically work better than any other fancy tricks that you use. And so this typically also outperforms Inception, just because you can just learn a much, much deeper network than Inception does. Right. So that's basically it. So these are three examples. I also recommend you to look at other examples, such as, for instance, MobileNet. MobileNet is a very useful network. It doesn't go any deeper, but it does all kinds of interesting tricks to do convolutions more cheaply. So it was meant to do deep learning on smartphones and so on. So it does all kinds of tricks to make computations much more efficiently. There are also models like ResNets or EfficientNet, and so these ones, so EfficientNet, these ones, they learn complex cells like this. Oh, sorry, like these guys here. But instead of constructing them manually, they learn them. So they will learn some complex set of um, layers and different connections, and they kind of learn this through data. So you would never come up with this by yourself. They just through data you optimize. You can use things like, well, like reinforcement learning or other things that just like there's a version based on evolution. There's a version based on gradient descent. Different ways that you can do that. And well, you would never come up by yourself, but you would just use them. Or well, you might actually also train them yourself if you want to. For particular cases, it might actually be useful to have custom neural networks for very particular cases. And if you have enough data, you can actually learn custom architectures just entirely from scratch.